So when you have the pressure increased by pushing this pressure pump downwards, you find out that you have reduced the amount of species inside. Even if the number of molecules of the gas remain the same, you reduce the species. And what have you done indirectly? You reduce the volume, because those amount of species inside the containing vessel actually amount for the volume of that gas. That's what accounts for the volume of the gas. So by that was how Boyle was able to postulate that there was an inverse relationship between pressure and volume. So the law states that what? That the volume of a fixed mass of gas is inversely proportional to the what? To the pressure, given that temperature remains constant. Given that temperature is kept what? Constant. So when we say temperature is kept constant, we're saying that temperature is not changing. And that simply means that Boyle's law will only operate under isothermal conditions. You know, in thermodynamics, we have different processes. We have isothermal process, isobaric process, and stuff like that. But Boyle's law is isothermal. Why? Because we said Boyle's law always will operate under situations where temperature does not change. And this iso here means constant. Thermal means heat, which is a function of the temperature. So that's that for the Boyle's law. So there's something we call Boyle's temperature. Boyle's temperature. Now, the Boyle's temperature is the temperature at which a non-ideal or real gas will begin behaving as an ideal gas. Will begin behaving, or we can say behaves as an ideal gas. Do you get that now? So Boyle's temperature is that temperature. We represent it as what? As TB. Boyle's temperature is that temperature in which a non-ideal or real gas behaves as an ideal gas. And it has an expression where we say TB is equals to A all over RB. I will explain this formula to you as time goes on, because these coefficients here are usually found when you are dealing with Van der Waals equation. They are coefficients. We'll look at them later on as the lecture goes by. Just keep this in mind. TB equals to A all over RB. R is your universal gas constant, and that's how you get the temperature, the Boyle's temperature, which is temperature where a non-ideal gas behaves as an ideal gas. JUPEB can just give you a question. At what temperature will this thing be able to behave as an ideal gas? And then you just need to pick out these parameters there, which I will soon give to you when we get to Van der Waals equation. Now, let's look at the graphing of Boyle's law. The graphing of Boyle's law. We have something like this now. I'm going to demonstrate with two graphs. So we have this. Let's assume that we have on our y-axis, let's put pressure there, or volume, anyone will work. So let's imagine I'm putting volume in this region here, and I put pressure here. And let's say maybe my volume is in centimeter cube. It can be in centimeter cube, dm cube, or liters. You understand? Your pressure, let's say we're working with atm here. Although we know we have atm, we have a millimeter mercury, we have torr, we have bar, and all of them like that, liters per meter square. But let's imagine we're working with this. So if you are plotting a graph of V against P, what kind of graph do you get? You should know, since we said as volume reduces, pressure will increase. That means if I'm starting from a high volume, that means pressure has to be low. You understand? For example, this point here. If you see this point here, whatever should be here is a high value for volume. And whatever is going to be here, when you trace it down, should be a low value for pressure. You can see that now. So high volume and low pressure. You know you're working with pressure on this side. So that is why the graph will look like this. Sorry, pardon me. It's going to look like this. So that's how the Boyle's law graph will look like when you're plotting volume against pressure. And this diagram here indicates that the line obtained when plotting the graph of V against B, or the line of Boyle's law, it shows that it is a rectangular hyperbola. Please keep that in mind. It's not a straight line. So it's a rectangular hyperbola with a negative gradient. So that's it, a negative gradient. You can see it goes like this. So it's a rectangular hyperbola with a negative gradient. But when you are plotting a graph of V against the inverse of P, or you are plotting P against the inverse of V, I want you guys to check this statement. When you have P inversely proportional to V, you know this statement here means pressure is inversely proportional to volume, and can also mean pressure is directly proportional to the inverse of volume. That is, P is directly proportional to the inverse of volume, like this, because 1 over V is still like this. So it means that if I am plotting a graph where one of the parameters is inverse, automatically I should be expecting a straight line. I should be expecting a positive line. I get now a line with positive gradient. So here now we're having positive gradient. So you only get this positive gradient when you are plotting V with inverse of P, or P with inverse of V. But when you are plotting V with P, you should be having a negative gradient. A negative gradient. Very important. So from Boyle's law now, where we said P varies inversely as V, we can bring in our constant of proportionality. And when we bring in our constant of proportionality, what do we get? We get what? We get P is equal to K over what? Over V. And then, making K the subject of formula, we have K is equal to what? PV, which implies that what? P1 V1 should be equal to what? P2 V2, continuous like that till you get to Pn Vn. So that's it. Constant. PV is a constant. That means no matter the multiplication of pressure and volume that you get, it should be constant. I get him now, given that your temperature is kept constant. So that's why we say P1 V1 is equal to P2 V2, and it continues like that. So that is that for your Boyle's law. Let's look at Charles' law. So Charles' law, on the other hand, was showing us the relationship between who and who, between the volume and the temperature. In this case, it is the pressure that is kept constant. Charles' law says that the volume of a fixed mass of gas is directly proportional to the absolute temperature. Key word there is that this temperature is absolute. And when we say it is absolute, it means it is measured in Kelvin. So whenever you are solving any question that has to do with ideal gas or any blah 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 like that, you should always take note that you do not work with temperature in degrees Celsius. You work with temperature in Kelvin, because we work with absolute temperature. Now we've said that this law only operates under where pressure is kept constant. So what thermodynamic process will Charles' law operate, or can Charles' law be tested? It can only be tested in an isobaric condition. Iso, like I said earlier, is constant, and when you hear the word bar, you can remind you of barometer, which is associated with pressure. That is instrument for measuring pressure. So isobaric here means pressure is constant, or constant pressure, and that's what Charles' law is saying should be the radar of its law, and then every other thing will be able to work given that this is constant. So that is what Charles' law is trying to say. That's the indication of Charles' law. All right, then let's look at the graph that emanates from Charles' law. But before we look at the graph, let's quickly look at the mathematics. So here now we can bring in your constant. So we have V is equals to what? KT. And then when you solve this, make K the subject of formula, you have K is equals to what? V over T. All these things are part of the things you probably have done in your O levels. And then we will now do what here? We can now make this a continuous case where V1 over T1 is equal to V2 over T2, and it's continuous, you get to Vn over Tn. So that's the case under this Charles' law. Let's look at two basic graphs of Charles' law. Let me look at two graphs that describe Charles' law. So the first graph is a graph where we are plotting. You know, in both of them, let's plot volume against temperature, volume against temperature. Let me use the blue. Let me use the blue marker on that. Volume against temperature, volume against temperature. Let me imagine my volume is in dm cube. So volume in dm cube, and temperature here in this part is in Kelvin, in this part is in degree Celsius. You can have the same what they call it, value graph pattern for the both of them, because we know that there is something we said here, that Charles' law only operates where temperature is in absolute condition, absolute scale. So This is direct proportionality. This means that whenever you increase the temperature, the volume is meant to increase. So when you increase temperature, volume is supposed to increase, which is rational. It's something you saw when you're dealing with thermal expansion. We know that whenever heat is added to a body, normal temperature will increase, and we say that when it is added to a body, the body tends to expand or increase in size. And since we know that the body will increase in size, automatically that implies that what? That implies that the volume, in terms of volume, that's cubic expansivity, it implies that the volume will actually get elevated or go up. So here now, it means that if I'm plotting against Kelvin, we are safe in this case. All I need to do is to draw a straight line. Are you getting it now? But in this case here, where you are plotting degrees Celsius, what you do here is this. You can't take it from here, because when we're plotting from this place, that's our 0 point. That's the point where volume is 0, temperature is 0. But in this case here now, we are plotting in a condition where what? Where our 0 here is no longer 0 Kelvin. It's now 273. It's no longer 0 Kelvin. Rather, it's 0 degrees Celsius. And we know that the graph has to start from 0 Kelvin. So where's our 0 Kelvin, which is absolute 0, is going to be at the negative side of this part. That means I have to go to a point where degrees Celsius is equivalent to 0 Kelvin. Are you getting me now? So that's where we are going to, and that should be at a point where degrees Celsius is minus 273. So if you check it, by the time you convert minus 273 to Kelvin, you'll be having what? 0. How? Minus 273 degrees Celsius plus 273. Because whenever you convert it to Kelvin, you have to add 273, and that gives us what? 0. So this is the point where we have to start our graph from. So we have something like this, which is still going to be a straight line. Do you understand that now? So that's that for that. That's that for that under the graphing of Charles' law. So the very similar thing happens in pressure law. Very similar thing happened in pressure law introduced by Gay-Lussac's. So pressure law. So in pressure law, we are just relating pressure with what? We are relating pressure with temperature. And you find out that whenever you increase the temperature, pressure also increases. This is a direct relationship. So we're having pressure is directly proportional to temperature, where volume is constant. Now, whenever you hear the word constant volume, it tells you that pressure law is operating under what we call isovolumic condition. All these things have thermodynamic implication. When you look at the thermodynamic equation, they have thermodynamic implications. So these isovolumic sometimes can also be referred to isochondric. So you have to make sure you are very careful when you are preparing for JUPEB examination. These are things that might take you off balance. But here at Magnificent Educational Consult, we make sure that all the concepts are being magnified without interrupting or reducing the complexity or the containment of that content. So very, 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 very important you guys think of this. So that's that for that. Then we have we said we will now look at how Boyle's law and Charles' law come together to actually form what we call the general gas law. So back here we have our Charles' law to say that V over T is its constant, while we have Boyle's law to say that Vp is its constant. So if we join these two together without repeating any of the parameters, that's where you have Vp over T is a constant. You understand that now? So Vp over T is a constant. That's why the general gas equation says that V1 P1 over T1 is equals to V2 P2 over what? Over T2. This is your general gas equation. General gas equation. That's the general gas equation. So it's just a combination of Charles' law and Boyle's law. And then it leads to what we call the ideal gas equation. The ideal gas equation says that what? It says that the product, the ideal gas equation, which is a law, it says that what? The product of pressure, you can always write it down, pause the video and write. The product of pressure and volume of a fixed mass of gas divided by its absolute temperature is a constant of that gas. And then upon scientific study, we found out that that constant K was actually equivalent to what we call NR, where N was the number of moles and R was the universal gas constant. So we have K is the NR. So by the time you substitute this NR in this place of K in the ideal gas equation, we'll be having PV over T is equals to NR is equals to NR. So when you cross multiply, you now have PV equals to nRT, which is the ideal gas equation that you are conversant with. So this R here, which is the universal gas constant, have two basic parameters, two basic constant values. So, but before I write it down, let's make R with something of formula here so that we can see something. R is equals to PV over NT. So from the lecture that we have in our playlist in physics under unit and measurements, you've been made to understand that if you want to write out the unit of this guy here, you have to just represent each of the quantities by their unit. Pressure is ATM, dot volume is what? Liters, and liters is still dm cube, so you can write dm cube there. Then you have N is what? Moles, and T is Kelvin. So it means that the unit of this thing here can actually be like this. Or if you want to look at PV as a single thing, PV is also referred to as the work done in a gaseous system. So that's the work of the gas. Are you getting me now? That's the work done by the gas. So if you don't want to represent PV now as ATM.L, you can call it joules, because PV is work. Are you getting me now? And work is measured in joules. So it's still the same thing as joules over what? Mole dot K. Are we getting it now? So R is ATM.liters per mole dot K, or what you call atmosphere.liters per mole dot Kelvin, or you call it joules per mole dot Kelvin. Are you getting that now? So when you are using this value, when you are using this first value here, then R will become 0.0821 approximately ATM.liter per mole dot Kelvin. But when you want to use this other parameter, you have 8.314 joules per mole dot Kelvin. That's this one here. So that's the two values constant for R, which is universal gas constant. This R is derivation, which we are even going to do in class on our online platform on WhatsApp. It's very, very simple. But if you want to find this value here, all you need to do is to use the standards of all these ones. P, you use 1 atm because standard temperature and pressure, standard pressure is 1 atm. So you use 1 atm here. In your volume, you use your what? The amount of volume of the gas occupied under standard temperature and pressure, which is 22.4 dm cube. So you have 22.4 dm cube here, which is equivalent to 22.4 liters. So divided by 1 mole is what we're considering here, and temperature 273. By the time you solve that math, you'll be arriving at this value here. So that's exactly how we go about it. So now we've been able to conclude on everything we are meant to talk about under the first session. So in our next video under this topic, in this playlist, we are going to be solving questions on all what we just did right now. So thank you very much.